Hello guys, this is category 1, page 26. These are the questions that have to do with Newton's laws of motion. So we're looking at, once again, page 26, question number 19. It says 4 students push carts filled with sports equipment across the gym. Each student pushes with the same amount of force. Which cart has the greatest change in speed? So then right here we need to pay attention that the carts are being pushed with the same amount of force. Remember what we said earlier. If we use the same force, the object with the least amount of mass is going to give us the greatest acceleration. So in this case, the greatest change in speed. So we need to look for the one with the least amount of mass. Right here, these are distractors. Don't look at the objects that are in there. So then this one has a mass of 10 kilograms, 20 kilograms, 15 kilograms, and 25 kilograms. So the smaller mass would be this one. So the correct answer is this one because of the small mass. This is still page 26 and it's number 43. So this one says the masses of 4 vehicles and the net forces acting on them as they enter the highway are recorded on the table below. So here's vehicles entering the highway. These are the vehicles, these are their masses, and these are the forces. Which vehicle has the greatest acceleration as it enters the highway? So I want the one with the greatest acceleration. If you look at the vehicles, guys, they all have different masses, but the forces are the same. It's similar question up on top. We look for the vehicle or for the car with the least amount of mass because they're being pushed with the same force. So right here, this is 1,500 kilograms, 1,200, 1,800, 2,000. So the smallest mass is going to be this one. So the coupe is the correct answer. So as you can see, these 2 questions had to do with the first law of motion. Okay, with the second law of motion. Okay, this had to do with the second law of motion, which is the law of force and acceleration. Now let's go to the next one. This is page 27. Okay, we're still with Newton's laws. Page 27, number 43. It says, a student jumps off a sled toward the west. So here's west. After it stops at the bottom of an icy hill. So then we have the student jumping towards the west after they stopped at the bottom of the hill. So then this one, the student jumped forward or towards the west, but as it jumped, we had right here the action-reaction force. My feet push forward and the sled gets pushed back. So push forward and the sled gets pushed back. So then, based on the law of action-reaction, in what direction will the sled most likely move as the student jumps up? So if the student moves west, then that means that the sled is going to go east in an opposite reaction. So then the correct answer is going to be east. So question 43 had to do with Newton's last law of motion, action-reaction. And if we see right here, we already, by looking at the picture, I got a feeling that this one has to do with action-reaction as well. Also Newton's third law. So page 28, number 48. It says NASA's space shuttle program was active from 1981 until 2011. The photograph shows rockets carrying space shuttle off the launch pad. So right here, launch of a space shuttle. How can Newton's law of action-reaction best be applied to explain the movement of a rocket? So action-reaction. Action going down, reaction being pushed up. with the same force. It says, as the fuel burns, gases push against the rocket, moving it upward. Okay, possible. As the fuel burns, gases move out of the rocket and reduce air resistance. They're not going to reduce air resistance. Air resistance will remain the same. As the fuel burns, the mass of the rocket decreases. The mass of the rocket cannot decrease because it's the same. As the fuel burns, the rocket moves faster. Right here, this doesn't give me any type of action reaction. So then let's go back to the first one. As the fuel burns, gases push against the rocket, moving it upward. Against the rocket, the gases, moving it upward. Equal and opposite direction. So the correct answer is letter F. Okay, now we're on page 29. So we're on page 29. We're still with Newton's laws. This is number 14. It says, during a demonstration of Newton's laws of motion, a student used the setup shown in figure 1. The student flicked the index card with the fingertip, and the coin fell straight down. So the coin fell down into a plastic cup shown in figure 2. So then coin was up here. We have right here the index card. And as soon as the card gets flicked, the card moves forward and the quarter or the coin goes down. So it was up here, card gets moved. What pulled it down, guys? Gravity, right? So gravity pulled it down. So which of the best explains why the coin fell straight down into the cup instead of remaining on the index card? So then right here, guys, I think that the coin wanted to stay up. It's staying up. An object at rest wants to stay at rest. But then what happened? They removed the index card. So then the object had to go down. So then the object now continued going down. So it fell into the container. Let's see what we have here. So which of these best explains why the coin fell? So why coin fell straight down into the cup instead of remaining on the index card? It says the coin was at rest until the card was removed, so it tended to remain in the same location. Once the card was gone, the unbalanced force of gravity caused the coin to fall. And that's similar to what we put right here, but I'm going to put a check mark. Let me see if there's a better one. Moving the card applied an action force to the coin. No, there was no action force right there. The card has less mass than the coin. So a smaller force of gravity. Now remember, gravity is going to be pulling with the same force. It's not a smaller one or a bigger one. So then right here, we're going to X that out. The acceleration of the coin falling into the cup was equal and in opposite to the acceleration of the card. No, the card moved sideways. Okay, so the correct answer is going to be letter F. That's our best possible answer. That's the correct one. This is page 30. So we have two questions here. Still working with Newton's laws of motion. So then the previous one that we saw was the law of inertia, law number 1. This one, let's see which law we're going to be working with. So this is number 14. It says the picture shows an aerialist walking on a tight rope and holding a balancing bar. So here we see the person moving on the rope and balancing on the bar. It says an action-reaction pair of forces exist between. So this one, I already know that we're talking about Newton's laws. Newton's third law. Action, reaction. Now, these forces, guys, need to be kind of like, I'm pushing you, you're pushing me. So they have to be touching, both forces need to be kind of like touching together. So it says, the aerialist's feet in the rope. You know what? I like that because the foot pushes the rope backwards and the rope pushes the aerialist forward. Kind of like when the student jumped off of the sled. Is the student or is the person jumped forward, the feet push the sled backwards. I like this one. So let's put a question mark. The rope and the balancing bar. The rope is not touching the balancing bar, so we cannot call it an action reaction. The two ends of the rope, they're not affecting the others, so no. The airless arms and legs. The arms and the legs, they're not connected. So then, right here, nope and nope. F is going to be the best possible answer. So let's look at the next one. On the next one, it says, a steel ball is at one end of the box that is moving forward as shown. So there we go. The ball's right here. The box suddenly stops. So then the box was moving, the person was moving. All of a sudden, they say, stop. What do you think is going to happen? This is law number 1. The ball is kind of like going at rest. The person stops, and then the ball is going to want to continue going forward in a straight line and at the same speed. But then what happens right here? Okay, according to Newton's first law, what happens to the steel ball just after the box stops? So the ball wants to go with the box, but the box stopped. So then let's see what the possible answers are. Because of friction, the ball continues rolling forward at the same speed. It wasn't friction, right? It was actually the stop of the motion of the box. So then, no. Because of the friction, the ball rolls forward at an increasing speed. We said that doesn't have to do with friction. Because of inertia. Inertia, remember we said it was law number 1? And that's the law of inertia, which says that an object at rest wants to stay at rest. The object was not at rest. The object was moving along with the box, but then the person stopped, or the box stopped. So now the ball was moving along with the box. Once the box stops, the ball wants to continue going. So then because of inertia, the ball continues rolling forward at the same speed. I like this one. Because of inertia, the ball rolls forward at an increasing speed. Sorry. So then right here, it says because of inertia, the ball rolls forward at an increasing speed. Not increasing speed. Remember, an object at rest wants to stay at rest, and an object in motion, which this one was in motion. Okay, an object in motion will continue in motion, going at the same speed and in a straight line unless acted upon by an unbalanced force. So then right here, the best possible answer is going to be letter H. Now, we're on page 31, and we still continue with Newton's laws of motion. So this one, number 15, it says, the unusual strength of a glue makes it able to hold a heavy object or load as shown in the diagram. So here's the board, here's the glue, and here's the load. So it says, if the load exerts a strong downward force, the glue, so this one, I kind of think it's going to do with action-reaction because they're pushing towards each other, the glue and the load. So then if the load exerts a strong downward force, so the load says, I want to go down, okay? So then the glue destroys the force. No, it doesn't destroy it. It's still there. Exerts a stronger downward force. No, actually the load has the downward force. Causes the load to accelerate upward. The object's not moving, there's no or there's no change in motion, it's still right there, so we cannot say that there's an acceleration. No, there's no acceleration. The glue exerts an upward force that is equal to the downward force. So then right here we have Newton's third law of motion. So then the load wants to go down, and the glue says, no, I'm going to hold you up, and they're exactly the same forces. So the correct answer is letter D. Let's go ahead and look at number 25. It says, two forces are applied to a 17 kilogram box as shown. the box is on a smooth surface. So then right here we have 35 newtons to the right and 18 newtons to the left. So then we have their opposite forces, so we're going to subtract 35 to the right and 18 newtons to the left. So then right here, I'm going to get my calculator. Because remember, we need to make sure that we do the calculations. And since we can use a calculator, I want you guys to use a calculator. Here we go. So then it's going to be 35 minus 18 equals 17. So I'm going to put right here 17 newtons. And I'm going to double check my work. So I'm going to clear right here. 35 minus 18 equals 17. So that is correct. Okay. So then we have 17 newtons to the right. To the right. Because this was my biggest force. Now let's go ahead and read the possible answers that we have right here. Now, by getting this information, are forces balanced or unbalanced? Remember we said anything greater than 0, we're going to say that forces are unbalanced. So I'm going to put that here. So that means that the object will accelerate. So I'm going to put, there's going to be acceleration. So let's read the information. Which statement best describes the acceleration of the box? A, the box accelerates at 1 meter per second to the right because the net force is 17 newtons to the right. Maybe. The box accelerates at 1.9 meters per second to the right because the greater force is to the right. Okay, so right here, as I'm reading, and as I'm reading, and sometimes this happens, guys, I need to make sure that I look for the acceleration of the box. So then what are we going to do? We're going to use the formula for acceleration. So I'm going to get my periodic table. Okay, so here's my formula chart. And force equals mass times accelerations right there. So let me go ahead and I have my formula triangle. So then let me go ahead and put here force equals MA. I'm going to fill in my triangle letter right next to the other one. So I'm going to put those down here. And the leftover F I'm going to put at the top. So then right here I have FMA. So let me see what they're giving me. I have the mass, which is 17 kilogram. And I have the net force, which is 17 newtons. So then right here again, I'm looking for the acceleration. So I cover the letter A. It's going to be F over M. So right here, it's going to be 17 over 17. So I'm going to get my calculator. And I'm going to put 17 over 17. So right here, oops. 17 divided by 17 equals 1. So then I'm going to put 1 right here. And right here, 1 meter per second. 1 meter per second square. That's going to be my acceleration. So right here, I immediately see that this one is 1 meter per second square. So I don't even need to go look at the other possible answers. There's my justification. Okay, so now I'm on page 32, still with Newton's laws of motion. So right here we have number 41. It says a pitcher throws a ball toward a player holding a softball bat. The player uses the bat to hit the ball. The ball applies a 10 Newton force to the ball. So then we have the bat, and the bat hits the ball. So bat right here, and this is the ball. So then I'm thinking action, reaction force. But let's see. Which statement correctly describes the reaction force, there we go, between the bat and the ball? The reaction force is the force that causes the ball to move towards the bat. No, it hasn't touched the bat yet. The reaction force is the force applied to the bat by the player. No, it's not being applied by the player. It needs to be applied by the ball. The reaction force is the force that pulls the ball towards the ground. No, that's gravitation. So no. The reaction force is the force of the ball on the bat. There we go. So then the correct answer is going to be letter D. Now let's go ahead and look at the next one. So this is number 26. 4 boxes are sliding with a constant speed. Before each box experiences an unbalanced force of 8 newtons. Which box would experience the greatest acceleration when the unbalanced force is applied? So then 4 boxes, constant speed. Before each box is applied an unbalanced force. Oh, all of them are being applied 8 newtons. So all of these are going to be getting a force of 8 newtons. So remember what we said? If we have the same force, the object with the least amount of mass is going to have the greatest acceleration. And that's what we're looking for. We're looking for the least mass. So then this one is 2 kilograms, 4 kilograms, 6 kilograms, and 8 kilograms. So then the best possible answer right here is going to be letter F. So right here, we're talking about Newton's second law. Over here, when we're talking about the bat, action, reaction. Action, reaction. So this was the third law. And then let's go ahead and go to the last one. This is number 16. A large rock is motionless, so the rock is not moving, on a flat sidewalk. Which statement best explains why the rock remains motionless? This is the law of inertia, guys, which is the first law. So there are no forces acting on the rock. There's always forces. Always forces. But that's not the reason why, right? Because they're saying there are no forces. There's always forces. So that cannot be correct. The only force acting on the rock is directed towards the sidewalk. No, why would it affect a force? If it's directed towards the sidewalk, how is it going to affect the rock? The force acting on the rock are all balanced. You know what? I like this one. All forces are balanced. So the object at rest wants to stay at rest unless acted upon by an unbalanced force. So if they're balanced, then it'll remain at rest. I like this one. The sidewalk exerts an unbalanced force on the rock. The sidewalk's just there. It's not doing anything unless someone broke a piece of it and it broke, and then it's affecting the rock. But that's not the case. So then, nope. The correct answer is going to be letter H. Okay. So then we just finished with all of Newton's laws of motion questions. See you guys.